Okay, so hello everyone, and welcome to our final session of contributed talks in the Algorithms and Software stream. I'm Curtis Bright. I'm a professor at the University of Windsor, so I'll be chairing today's session. So we have four speakers today. Each speaker will be giving 15 minutes with the warning in the chat and at around 12 minutes. So our first speaker is Dr. Aliev, and you can begin.
The topic is the number of inscribed and circumscribed graphs of a convex polyhedron. I used Maple in this research. So let us first start with some definitions. Imagine we have a polyhedron, convex polyhedron. On each edge of this polyhedron, we take a point and connect them in a natural way to get another graph. So by graph, we mean a one skeleton, which is the vertices and edges of a polyhedron. So when we take these points and connect them, we get a one skeleton. And into this one skeleton, we can inscribe another one skeleton or graph. And the question that I will ask here is, what is the maximum of the number of graphs which are inscribed into a fixed graph? Here it is red, and circumscribed around another graph, which is here is green. So how many graphs like this blue one do we have, which are inscribed into red and circumscribed about green? The answer to this question is 4. And you see here an example where this number 4 is realized. It is an octahedron inside of which we have another graph and into which we inscribed another graph, green one. And the number of blue polyhedra is 4 here, exactly 4. Before solving this problem, we should solve a planar problem. On plane, imagine you have a polygon, A1, A2, etc. You inscribe into it B1, B2, etc. And into B1, B2, etc., you inscribe C1, C2, etc. Now you can ask similar question for this planar problem. How many polygons like B1, B2 are there, which are inscribed into A1, A2, etc., and circumscribed about C0, C1, C2, etc.? The answer is, again, 4. I will show you examples and proof. This planar problem has long history. Poncelet, in his paper Application d'analyse et de géométrie, which published is in 1864, he considered this problem. My French is not good, but one can read from here that Poncelet takes the vertices x prime, x double prime, etc. on fixed lines, except one of its vertices, alpha, and he forces all the sides of this polygon to contain the given vertices a prime, a double prime, etc. So Poncelet in this work proves that this vertex moves along a conic. Poncelet was interested with these problems because of his porisms. Maybe some of you know there are interesting theorems which are called porisms, where you prove that if a certain polygon exists, which is inscribed into one object and circumscribed around another object, then there are infinitely many of them, porism theorems. Poncelet came up with this question when he was soldier in Napoleonic army in Saratov as a prisoner of war. Poncelet cites earlier work by Briançon, Solution de plusieurs problèmes de géométrie, which was published in 1810. The same problem. And Briançon cites even earlier works from 18th century by Breckinridge and Maclaurin. So the history is the history is very long. So back to the planar problem. How many polygons do we have, which are inscribed into one and circumscribed around another one? I give an example with regular polygons and show that there are 4 such regular polygons. It is possible to find 4 such polygons. If you take this regular polygon and this polygon here with distance x, you might notice that as x increases, this starts first to increase, this distance EI, CI, and then starts to decrease. So you can find 2 points where they get the same result, same length. Mirror image gives another pair. So you have 4 such polygons. And then another example, which I found using Maple. I want to stop sharing for a couple of seconds and go to Chrome. So this is example that I did on GeoGebra, but the mathematics behind this example is done in Maple. So here you have 4 polygons, but these 4 polygons are changing as we change parameters. And this works for any n. The mathematics behind this more general example was done using Maple. I can return to my sliders, make full screen again. So we have examples when there are 4 polygons. Why can't we have more than 4? I used this inequality, elementary inequality, that BF divided by FE is greater than the hash divided by hash. I cannot see the letter hash C. Yes. Its proof is elementary. You can just draw this parallel line to DC and use Menelaus theorem. Immediately the result follows. Now, if you will look at this picture, imagine you already constructed one from in this direction and another one in this direction. You can use our lemma and prove that you can't have another one like this because of the lemma. If you have another one, then the ratio here is greater than ratio here, which is greater than ratio here, and you go in a cyclic way and return to the same ratio. So ratio is greater than itself, which is impossible. Similar result on this orientation. So you have only 2 here and 2 here. That's why maximum 4. Of course, there are details of this proof, and I gave them in my paper. We can continue. So this result can be generalized immediately for spherical and hyperbolic geometries using these projections that I took from Klein-Rosemann book. One can show that since the result is true for plane and polygons, it should be automatically true for spherical polygons, convex polygons, and hyperbolic polygons in hyperbolic geometry. So we can go back to our space problem. Why we can't have more than 4 polyhedra? Because on each face of this polyhedra, we have polygons inscribed into each other. And we already know that the maximum number of polygons is 4. That's why maximum number of graphs is inscribed into convex polyhedra cannot be more than 4. And 4 is realized, as you see in this picture, for octahedron. I also tried to prove Maclaurin and Breckenridge's method of conic generation, which can be used to prove the part about the maximum number is 2 in one direction. So it follows from the fact that if you take big triangle and small triangle, and then this black triangle, 2 vertices of which are on the sides, and all the sides contain the given blue points, then the free vertex moves along a conic. So this is direct consequence of Pascal's theorem. I generalized it And you can also consider the problem in more general context, not just convex polygons, but polygons considered as collection of lines and vertices, which are points. Then the answer, of course, increases, and the number is, in this case, n factorial, n minus 1 factorial, total number of polygons inscribed into one, circumscribed around another one. Here, n is 3. So in total, there are 3 factorial multiplied by 2 factorial, which is 12. 6 red, 6 blue triangles inscribed into one black polygon and circumscribed around another polygon, which are these 3 vertices. To draw the pictures, I needed a construction algorithm, and I found construction algorithm for these vertices. Here you see the generalized Maclaurin and Breckenridge's conic generation method, and I proved it using mathematical induction. The proof is in the paper. One might ask, why octahedron, not other Platonic solids? Why can't we do this example on other Platonic solids like this tetrahedron and this cube? Of course, one can do this, but we do not get example that we wanted, because the number of faces meeting at each vertex is odd here. So our example will not work because it alternates and we don't have closed loop after 3 iterations. Same problem here. So cube and tetrahedron, of course, these pictures enjoy many symmetries, but it is not an example. Same problem for dodecahedron and icosahedron. The number of faces or edges meeting at each vertex is odd, and therefore we cannot use these pictures as examples. One can try to do for non-convex polyhedra, just glue together many octahedron, and at each vertex you have either 4 faces meeting or 6 faces meeting. So we can use that same idea that we used in octahedron to create arbitrarily large non-convex polyhedra with an example. I also found different other non-convex polyhedra. I couldn't do this. I couldn't draw these pictures in computer, but I created physical model using this geomac pieces, magnet pieces. So at each vertex, even number of faces meet. For example, here 4, here 6, and therefore we can use this as an example. Another such polyhedron, non-convex polyhedron, is here on the right. One can also apply this idea for grids, hexagonal, square, and triangular grids. In general, one can think of these grids as polyhedra of infinite volume. So they are not closed, but extend on a plane. So if we will use the same idea, we get these pictures. For hexagonal, for square, and for triangular grids, we get this picture. And the answer is still the same. The total number of blue grids inscribed into black one and circumscribed around red one is 4. Maximum number is 4. And 4 is realized, for example, in this picture. Same here and here. There are many open problems, interesting problems that one can think about, work on. Is it always possible to inscribe 4 convex polygons into any given convex polygon so that all 4 are circumscribed around another convex polygon? So we found examples, special examples. What about given convex polygon and trying to find 4 such convex polygons? Is it always possible? And there are many other questions like this that can be interesting for the mathematicians, geometers. Thank you. This was my last slide.
Thank you, Dr. Alev, for the interesting talk. Are there any questions? We have about a minute.
I guess one question I was thinking of is, does this generalize to higher dimensions? Have you looked at polytopes in higher dimensions?
Yes, very good question, Eric. Actually, it is one of the questions that I put here. I'm not a specialist in higher dimensions. When I tried to work with higher dimensions, I saw that I make many mistakes, so I gave up with higher dimensions. I'm not a specialist, but it can be interesting for geometers. So I tried to work with 4 dimensions, but I noticed that it is not that trivial, not so easy.
Okay, then I should thank you again. I liked your worksheet with the moving points.
Yes,
so let's
stop the sharing.
Yeah, stop sharing, please, and move to Dr. Huang. All right, Dr. Huang from the University of Hong Kong, please go ahead.
Let me introduce the main objective of this work. We know that the integrability problem of rational planar ODE, where Mn belongs to polynomial in real number field, is of considerable interest in research area of dynamical system, physics, etc. And we know that many solvable types, including Riccati, Abel, Bernoulli, Cini, etc., recognized by the powerful maple dissolve command, share the similar structure. And this type of ODE remains its structure under rational linear transformation. And basic solvable type applying any linear transformation classifies a solvable equivalent class of such ODE according to invariant and symmetry theory. However, if the transformation being applied is a general nonlinear one in terms of the dependent variable y, it no longer maintains the structure, and the integrability in general could no longer be detected by the existing maple dissolve command. And after the transformation, the ODE will have a more complicated structure of the following form. And to summarize, for given rational ODE, our goal is to design an algorithm based on maple to find any possible AXY, BXY, FIX, TX, if exists and may not be unique, such that these two equalities satisfy. And here I want to emphasize a crucial assumption for this algorithm is that M and N has to be co-prime and could be expressed in terms of polynomial AB, FIT in such form. If M and N are not co-prime and some common factors are cancelled, then this algorithm may fail in some cases. And in these 2 papers, authors have stated method for detecting integrability for this type of ODE when n is less or equal than 2. And instead of detecting the transformation, they use method of inverse integrating factor. We would like to generalize this method to n is arbitrarily large. And when n is bigger than 2, we use a unified method to detect the possible value of n, a, b, as well as the reduced solvable ODE. And there are actually many things to review. Many things can be reviewed about the integrable type in such ODE, but I mainly want to highlight the Abel differential equation, since we are going to use it in the code demonstration. And let's introduce the Abel differential equation. It is defined in this form, and the solving scheme for rational Abel differential equation is based on the invariant theory. The invariant is calculated from FIX. When the invariant is constant, the Abel differential equation is integrated by quadrature. When the invariant depends on x, Maple tries to use the invariant to review linear transformation that transform the equation to solvable type, which are mentioned in Kempker Murphy's book and in this paper. And I also want to mention about the power Abel differential equation. The differential equation of the following form can be reduced to Abel differential equation by a simple power transformation. And for an equation of the following form, if we apply a linear transformation where fx is undetermined, if the equation can be transformed to power Abel equation under linear transformation, then all these terms will share the common solution fx. We may try to solve for the rational solution in any one of these except for f0. If we obtain the solution, we substitute into the other to check if they equal 0 simultaneously. And I also want to mention about the algebraic invariant curve. Without knowing any information about the general integrability, mathematicians are also very interested in finding the algebraic invariant curve. In some trivial cases, the algebraic invariant curve could be directly detected using Maple's algorithm. But in general, the algebraic invariant curve is very hard to detect. Usually, the user needs to specify the degree for the algebraic invariant curve and use method of undetermined coefficients to compute the algebraic invariant curve. The meaning of this algorithm is that if we successfully reduce a complicated differential equation to this relatively more simple structure, its algebraic invariant curve may have lower degree and may be easier to verify. So now I'm going to introduce the algorithm. We divided all the cases into two subcases. The derivative of b with respect to y equals to 0 and does not equals to 0. If it equals 0, then this case will be trivial and could be quickly examined. If it does not equals to 0, then we divided this case into n is less or equal than 2 and n is bigger than 2. For n is less or equal than 2, we impose it to have an inverse integrating factor with some undetermined functions. For n is bigger than 2, we try to find the reduction transformation that reduces the nonlinear ODE to more simple structure. We first handle the trivial case. Suppose we factor n into n0 multiplies n1, and j equals to the degree of y in n1, I equals to the degree of y in n. Then we set axy equals to this value, bxy equals to 1, tx equals to n0. And if I divided by j plus 1 is an integer, we set n equals to I divided by j plus 1. If it is not an integer, we can exclude this case. And we try to solve the following equality for Fix. And the equations for Fix will be linear equation. If no solution exists for the linear equation systems, we can exclude the trivial case. And when n is less or equal than 2, there's a theorem. Suppose the differential equation satisfies this form. Then the differential equation will have an inverse integrating factor of the following form, where Qx is defined by Fix and omega x is the solution for the corresponding linear ODE, where the Riccati differential equation is equivalent to. Suppose I equals the degree of y in n, j equals the degree of y in n. To detect such type of inverse integrating factor, we may assume it has the following form: to be a square of a polynomial in terms of y and with some undetermined functions, and the degree of the polynomial is bounded by this value. And if we substitute into the condition where the inverse integrating factor satisfy to solve for the coefficients functions, the equations can be reduced to a homogeneous linear differential equation with differential order at most 2, and this is proven in this paper. And if we find non-trivial solution, we will obtain an integrating factor for the original equation. And when n is bigger than 2, we use a unified method to find the reduction transformation. The algorithm is going to first decide, based on the degree of y in Mn, the possible degree of n, the degree of y in A, the degree of y in B. The polynomial nxy needs to be factored over real number field. And from all the factors that depend on y, based on the guess degree of A, B, and n, the algorithm is going to select possible factors of polynomial B based on their multiplicity. And with all the possible factors of B, we use a backtracking algorithm to construct possible candidate for B. And with B being assigned to the possible candidate, we set A equals to a polynomial in terms of y and with some undetermined functions AIX, and we try to solve for the AIX in this following equality. And since B is fixed to the possible candidate, the equation for AIX will be reduced to linear equation. But some candidate for B may not lead to solution. To quickly exclude these candidates, we use numerical evaluation. We insert value to x and other symbol appear in the differential equation. The limitation for the numerical evaluation value is that the highest degree term of y in n doesn't vanish. We first check if the numerical solution, which means value at a given point for AIX exists. If it exists, we continue to solve for the symbolic solution for AIX and Fix. And this is the pseudo code for finding reduction transformation. And now I'm going to do a simple code demonstration. And at first, let me introduce the method of inverse integrating factor. Now I have a Riccati differential equation which can be solved in terms of every function. And if we try to apply a nonlinear rational transformation to its dependent variable, it becomes a more complicated differential equation which cannot be directly solved by Maple. If I assume it has an inverse integrating factor of the form I mentioned and substitute the inverse integrating factor into the condition, the coefficients in the inverse integrating factor can be solved by the dissolve command, and the coefficient is expressed by the array function, and you can use it to construct the solution for the differential equation. And then I'm going to introduce the algorithm for finding reduction transformation. Now I have a power Abel differential equation, which also has solutions in terms of special function. If I apply a nonlinear transformation to its dependent variable, it becomes a more complicated differential equation. And I write a program called degree test. And the degree test is going to tell, based on the numerator polynomial m as well as the denominator polynomial n, the possible value of n, the possible degree of a in y, as well as the possible degree of b in y. And it computes finite many possible cases. And for some cases, for example, this one, since no qualified candidate for B is found, it is actually invalid. We can exclude it. And the actual correct case is this one. And for some case, for example, this one, we need to use the numerical evaluation to exclude it. For example, if we try to solve the numerical solution at the numerical evaluation point x equals to 1, we verify that the numerical solution at this given point does not exist, which indicates the symbolic solution also could not exist either. And for the correct case, we successfully obtain the numerical solution, which indicates that we can continue to solve for the symbolic solution for in the transformation and the reduced ODE. And for ODE of this structure, like I have mentioned, we can test algorithmically very easily whether it is equivalent to power Abel equation under linear transformation. And we successfully solve for the linear transformation, and we reduce it to power Abel equation and then to Abel differential equation. And eventually, the Abel differential equation can be directly solved by the dissolve command. And we back substitute all the variables to obtain the general solution for the complicated ODE and use ODE test to verify the result is correct. So this is the end of the code demonstration. And this is the end of my presentation. And thank you guys for listening. And this is the reference.
Well, thank you very much, Dr. Huang. I don't think we can see the reference, but are there any questions?
If we have time, I have one quick question. This is Austin Roche speaking. This looks great, I think. It's hard to follow all the details because there's a lot of details, but I'm just wondering, did you find any applications? Did you find any kind of ODEs out in the wild that you were able to solve with this, or all the examples that you have kind of contrived?
No. It's great honor to have you here, Dr. Austin Roche, and I haven't find any applications of the question I studied.
Okay. No, that's fine. I mean, I imagine that it's difficult because
I don't think I find any applications of this.
Yeah, it's still nice to have improved generalizations of the existing technology. So that this is really great. Thank you.
Okay, then we should move on to our third talk. Thank you again, Dr. Huang. So could you stop sharing your screen, please? And next we have Dr. Haju. Could you share? Yes, here we are. All right, and our next speaker would be Dr. Flora Hajdu, or Hajdu. Go ahead, please.
Okay, so welcome everyone. I am Dr. Flora Hajdu from Széchenyi István University, Győr, Hungary, and my topic will be parallelization of the one-at-a-time sensitivity study of nonlinear systems using Maple. And here is the content of my presentation. First, I will discuss about the research background, then the parallelization possibilities with Maple, then briefly describe the sensitivity study and the examine system. Then I will tell you about the parallel program. Then I will tell you about the results I got, and I will end the presentation with further research tasks. So the research background is that the parallel creation of phase space and phase space diagrams of nonlinear system was already carried out with Maple, and the parallel creation of two parametric bifurcation diagram as well. And using a simple personal computer with 4 nodes over a 3 times speed up could be achieved with an efficiency almost 90%, which gave me the idea to continue parallelization and carry out the parallelization of one-at-a-time sensitivity study of nonlinear systems as well. So Maple provides 2 possibilities of parallelization: the task programming model, which is thread-based, and the grid programming model, which is multiple process parallelism. And based on my previous experience, because task programming model was interfered and it was slower than grid programming model was selected for further research. And here you can see the sensitivity study. So first we need to specify the parameters and the output variable and solve the differential equations numerically. Then we can calculate the output variable, which can create the sensitivity diagram. And then we can calculate the sensitivity index based on the sensitivity diagram. And we need to calculate the membership to the sensitivity sets using Maple's Diffusify package. For this, we need to divide the sensitivity function into segments and calculate their membership. And here you can see an example for the centroid for the diffusification using Maple's fuzzy set 3 domain package, and then calculate the sensitivity number with Maple's Diffusify. And here you can see the examined systems. First, the Duffing type vibration system with the excitation force, which consists of an amplitude and the angular velocity, and then a nonlinear spring and the damper, and the fire truck suspension system with nonlinear spring and damper characteristics. And for the Duffing type vibration system, all of the parameters were examined. For the fire truck suspension system, because it has a lot of parameters, only the mass of the superstructure was examined. And here you can see the serial program. It is as we have discussed it before. So we need to create the selected parameters, which is stored in a list. And then we solve all the differential equations with different parameters. And then we collect the results in a list. And then we create the sensitivity function from that. And then we create the one-at-a-time, we carry out the one-at-a-time sensitivity study with fuzzy sets, and then we can get the sensitivity number. And as the tasks are independent the parameters are independent from each other, these tasks can be easily parallelized. And here you can see the parallel program. For that, we use a master node, which sends the parameters to the slave nodes. And the slave nodes do the calculations and the numerical calculations. And then they send back the results to the master node. And here you can, and all of the cases, the root mean square of acceleration was selected as the output variable. And this task was tested on a gamer laptop with an Intel Core processor with 8 nodes. And here you can see the results of parameter n. You can see that as the number of parameters increased, the speed up and the efficiency decreased. And the best results could be achieved using 4 nodes, which was around 80% efficiency, but 6 nodes also gave good results, over 70% efficiency. And here you can see the results of parameter C. It is very similar to the previous one. And here you can see the results of parameter K. It is also similar to the previous one. So the best efficiency could be achieved in case of 4 nodes. And parameter A the results are also similar. And for parameter omega, the results are also similar to the previous case. And here you can see the overall results. You can see that the best speed up could be achieved in case of parameter K. And with the number of parameters, the best speed up could be achieved in case of 1,200 parameters. And in all cases, the speed up and the efficiency decreased as the number of parameters increased, except of parameter omega. In this case, the speed up decreased first, but then it increased. And you can see here the scalability studies. So the calculation time decreased as the number of nodes increased. But after a while, after 6 nodes, it decreased not that much. And in case of the speed up increased when the number of nodes increased, but not in a linear way. You can see the efficiency in the number of nodes was 4, then the best efficiency could be achieved in that case. And as the results were similar in case of all the parameters, the FireTrack suspension system was only tested with one parameter, as it has a lot of different parameter combinations. And you can see that as the parameters increased, both the speed up and the efficiency decreased, but still 60% efficiency could be achieved in case of 8 nodes, and the best efficiency could be achieved in case of 4 nodes, but using 6 nodes resulted in over 70% efficiency. And here you can see the diagrams. You can see that the speed up first and both the speed up and the efficiency first increased, and then it decreased as the number of parameters was increased, and then it increased again. And the speed up also increased when the number of nodes was increased, but after a while, not that much. And in case of the number of nodes was increased, then the efficiency decreased after a while, and the best efficiency could be achieved using 4 nodes. So to summarize, it can be seen that one-at-a-time sensitivity study of nonlinear systems can be parallelized, and the parallel program was tested with 2 systems. Using 8 nodes, around 60% efficiency could be achieved, which means around 5 times speed up. The best efficiency could be achieved using 4 nodes, which is around 85% efficiency. But the optimal solution seems 6 nodes on the tested laptop, which is around 70% efficiency. And further research task is the parallelization of one-at-a-time sensitivity study of nonlinear systems using a computer with more nodes, and the one-at-a-time sensitivity study of other complex nonlinear systems using Maple, like, for example, robots. And if possible, then utilizing Maple's grid computing toolbox, so even more computation power can be achieved. So I would like to thank you for your attention, and I'm waiting for your questions.
All right, thank you for the interesting talk. We have several minutes for questions, if anyone has some. Anyone? I guess I have a question. So you had this FireTruck suspension system. So I don't know much about this problem. What is it you're actually computing about the system?
The vibrations of the FireTruck, so the root mean square of acceleration of the main body. So we can get the harmful vibrations of the FireTruck.
Okay, so you're computing how, for the various parameters, how much the vibration will be in the
Yes, exactly. And that's why we need the sensitivity study as well.
Okay, and your parallelization. So the efficiency was how many, with 8 extra cores, you have a speed up of 5 or something, and so that you just divide those to get the
8.
efficiency. So it'd be 5 divided by 8.
No, so it was tested on a computer with 8 nodes.
8. But if you had a
8.
speed up of 5, it would be like a
Yes.
5 divided by, okay, for efficiency. Any other questions? If not, let's thank the speaker again and move on to our final talk.
Thank you.
My name is Faladi Kazim from the Department of Mathematics, Faculty of Computing and Mathematical Sciences, Aliko Dangote University of Science and Technology, Wudi, Kano State, Nigeria. I'm here to present our article titled Algorithm Approach for solving time fractional coupled system of partial differential equation. Abstract. In this paper, we introduce and apply an efficient computational algorithm, utilizing the capability of the Maple-18 software package, incorporating the coded fractional derivatives in the Riemann-Loewis sense. Our focus is on solving coupled system of partial differential equations commonly encountered in engineering and mathematical physics, such as fluid dynamics, viscoelastic material, Cisco damping, polymer physics, and just to mention a few. Our proposed algorithm uses various mathematical commands within the Maple software package, and they will presented 4 illustrative examples of both linear and non-linear system of equation. The obtained result is presented in a systematical way where we compare our results with the exact solution, and then which we present our results in 2D and 3D graphs. The proposed algorithm is characterized by it is very simple, easy, reliable, and efficient. It holds the potential to serve as a valuable mathematical tools for addressing a wide range of systems of partial differential equation in applied mathematics. Introduction. Time fractional partial differential equations have gained significant attention in areas of engineering and applied mathematics. Its application to model various physical processes, such as heat conduction in composite material, non-nonlinear fluid dynamics, viscoelastic behaviors in the structural elements in the group, and all these can be found in our references 1 to 4. In this paper, we present and apply computational techniques to solve linear and non-linear system of 2 dimensions that result from the time fractional partial differential equation in damping, symmetric analysis, viscoelastic material. And that can be even found in our references 5 to 6. In this case, we have equation 1. Equation 1 is a partial differential system of partial differential equation, which has U, V, W, and Z as dependent variable, and the independent variable of X and Y. And then the fractional here, which is the derivative, the fractional derivative we have, which even less than or equal to 1, but has to greater than 0, has to greater than 0, is within that range, which subjects to the initial condition of G naught, which is X, Y, GY 1, S, Y, G2, S, Y to GK, S, Y. And then where they are smooth function. We have what we call definition of fractional calculus. In this case, we have equation 3 and 4, which they are Riemann-Liouville and the Caputo derivative of alpha, which is greater than 0. And the equation 3 and 4 is the type of ODE. We use this for one variable function, which is the one of UT. But in the case where we have partial differential equation, we are going to consider equation 5 and 6, which is definition 1.3 and 1.4. These are the type of Riemann and the Caputo derivative for partial differential equation. Literature review. In the recent year, time fractional system of partial differential have gained a significant attention in making modeling complex phenomena in the areas of mathematics and physics. This phenomenon encompasses a wide range of polynomial physics and physical elastic behaviors, which can be found in the damping, viscosity damping. And then several authors like author 8, he has even worked, several authors have even worked on this. Like author 8 came up with the method to solve this type of problem. The same thing method, reference 9, propose an efficient computational scheme to solve this type of problem. Author 10 also came up with another method to solve this type of problem. And then where use initial boundary value problem was used by author 11. And then we also have author 12, 13, and 14. All these authors, they have recently, in the recent time, they have even worked on this type of problem, which has even been our references for this work. And then we want to look at many of the work, the methods are very okay. They are very okay. They are very good in terms of accuracy. But so we in our own case want to come basically to use Maple software, to use purely Maple software package to come up with the techniques, which we call 10-step algorithm, description of the computational algorithm. 10-step algorithm we have. In this case, we consider equation 1 and 2, which we have stated from our previous slide. And then we have what we call stage 1. Stage 1 is what we call initialization. We initialize the worksheet at the beginning, because that one will build up. That the step 1 is a build up of what we are going to have in the other steps. And then in this case, we consider digits. Digits in this case is what the decimal we want our result to be, whether it is to be in 2 decimal, 3 decimal, or 4 decimal. And the n in this case is what we call computational length. Computational length is where we have a point where we have the best results. We have to suggest that at the beginning. And then we have the command, the equation 5, which is the Riemann definitions. We have to put it at the beginning. And then we subject our equation 2, which is the initial condition. And in this case, we have U0, V0, and W0. And then we have step 2. Step 2 is operator stage, where we make an operator A, B, C to have in the form of our problem, which is equation 1 in this case. And so when we look at the step 2 is where we have a prototype of our problem, so that by the time we run it, and then we should not even, we have seen that even the condition 2, which is equation 2, is that of the initial, what we have as initialization in that in step 1. So step 2 is we have operator A, B, C, which stand for that prototype of that problem we have. And then the next is that of the A1, B1, and C1. A1 and B1, C1, they are the decomposed ABC. The ABC is now decomposed in form of a transformed to A1. A will not transform to A1. B will not transform to B1. And the C will also transform to B1 in that step 3. In step 3. And then when we look at that step 3, we have seen here that we have n-1 throughout for that step 3. So in step 4, we have to have another decomposed A1. So A1 have decomposed inside that A2. B1 has also decomposed to B2. Where C1 has also decomposed to C2. And in that case, we subtract n-1, we now change to n-2. And then the reason why we have this n-1 and n-2 is basically because we are into x, y as an independent variable. N1 and C1, in this case, n-1 and -2 is because we have 2 independent variables. In the situation where we have 3 independent variables, so we still need to have A3, B3, and C3. But in our own case, we have N1 and N2. Step 5 is where we try to have a false result. We must have false result because at the beginning, these are these processes of getting the initial to be decomposed together and transform. So the first stage at the stage 5 is to have the result at for n from 1 to 1. We want to have the first result. And then whereby the step 6, we want to have a situation whereby n from 2 to n. And I've said it earlier, in this case, n is a certain number. A finite number that we have to make our first attempt. Because it's very simple. If n is 10, if the result is not okay at then 10, we increase it to 11 or 12 so that we can compare our result with the exact solution. Step 7 is to have a result. We have a solution for solution U, V, and W. And therefore, that of the step 8 is to have the numerical result. There's opportunity for us in this algorithm to have what we call results in a tabular form. We can have that one in a tabular form. And then after that, we have step 9. Step 9 is to compare our results in form of absolute error. We have to compare our results. So we compare exact solution of U with our proposed method of U. And the same thing for V. We do the same thing for W. And then that is even stage 9. At the stage 10, which is the last stage, is where we plot the graph. This is the environment for the graph. And then these are the commands, purely Maple commands that we use to generate results with different colors and every other thing. And then our result can be seen from the graph and the appendix that we have. And then in this case, we have the implementation of this problem. Of this, what we have even formulated. We have to test it and see whether our technique is okay or not. So we have references 8, 9, 19, and to 20. And then we have this equation 7. And then we have UVW with the fractional of alpha, beta, and theta. We have the conditions are given in 8. And then we have the exact solution, which according to the references we quoted above, they are of that or at when alpha, beta, and theta, they are 1. Then we have the exact solution. We compare this, our result. We use the techniques we proposed. And then so we have results which is presented in that A1 to 1G. In a similar way, we compare, we have the problem 2, which is that equation 10, 11, and 12. And the exact solution is given at 12. We also have the same, we did the same thing. We run the algorithm and we compare our results with the exact solution, and the result was okay. And then we have problem 3 too, which is the equation 13, 14, and 15. In this 15 are the exact solution given from the literature. Then our results are okay, which are presentable, and they are the same or probably in good agreement. And then the last problem is Bogart equation. We consider this Bogart equation in the sense that it's a special equation, and then that can be found in our reference 21. And then equation 16, 17, and equation 18 is the exact solution. and which we have our results presented in the 2D and 3D graphs. And in this case, this is the problem 1. We have the 2D problem. We can see U at alpha is 0.2. We obtain the minimum result or minimum solution. Where the integer is the blue, when alpha is 1, which is according to the literature. So this is the result they obtain from their literature. So all these are and then we can see here, the fractional one is the least one when alpha is 0.2. But the other way around, according to the literature, this is their results. But the fractional, we have alpha is 0.2 is the maximum for U. And similarly for the V. For the V, we also have the same process. We also have the same process, which is also and then this is the integer, according to the literature, that we compare our results. And obviously, this is the 3D plot for the example 1. And then we have seen here that this is the integer, this is the least, which is alpha is 0.2. But in the other way around for V, the beta, in this case, when it is 0.2, is the highest. And then similarly for the W, we have the highest here, and then which is concord with our 2D graph. The Serero says that alpha is the least, and then the beta and the theta, they are the highest when it's 0.2 in that manner. And then we have another problem of problem 2. This is the problem 2. And then we can see here that our alpha is 0.2 is the least result. And whereby for the beta 0.2 again, that is when alpha and beta is 0.2. We have the least results, and then which is an integer according to the literature. This is their results, and then according to the literature, so you can see it. And then the same vein, we also have the 3D for the example 2. For the example 2, we have the 2D, which is demonstrated the 3D surface solution for that problem 2. In a similar way, we have the problem 3. In this problem 3, alpha is 0.2, where the beta is 0.2 is in the intermediate. It's not even least, it's not even the maximum, it's not the minimum, but the result is at the intermediate. We have the graph for the 3D, which is exhibited. This is the relationship between the U and V as a system of partial differential equation. This graph 3A is giving us their relationship. And then we have the other one. And then the bogus one is this. This is the literature results, which is blue. Our own results are the black, yellow, green, and red. And then we can see here the 0.2 is the maximum for both. But the one of V is the highest when alpha and beta, they are equal. So we have this. And then the last graph, which is this, is giving us the laminar and turbulent flow. But this is a bugger problem. And then we can see the relationship between the U and V. In this case, we can see the graph is in form of a turbulence. Yeah, it's in form of turbulence. And then the same thing is in form of a layer here, which is also turbulent flow in form of a waves. In form of waves. We have of the U, we have of the V. And then from the discussion, we can see from the discussion all the scenario, the study focus on formulation and its implementation of the algorithm. For the soft type purpose system of partial differentiation, we have even said it. The result for figure A to 4 is depict the integer. Where the integers are there, we can see the results show the decrease in numerical solution. That is from the blue, which is the highest to the least. But in the same, in another scenario, is reverse the case when the result obtained show the decrease in numerical solution for the same problem, but different solutions. So we try to compare our results together and see But we have even established one thing here, that our algorithm is very superb, at the same time is comparable with the existing method. Conclusion. This paper has demonstrated a significant advancement in the field of computational mathematics, especially in the areas of time fractional coupled system of partial differential equation. The algorithm strike a remarkable balance between the computational efficiency and accuracy by reducing the new techniques and integrating the best usage of Maple software package. The creation of the novel algorithm has created opportunities for additional research and use in the varieties of scientific and engineering field. In addition to offer the dependable computational tools for handle challenges that we normally face in the fractional order or fractional problem. The paper effectively tackled the difficulties in some problem that we consider, which is the system of, because it's not easy to solve a system of equation, particularly the nonlinear. So, and then our algorithm really demonstrated they're very fast to run, easy to run, easy to code, and they're easy to execute. However, the algorithm opened a new door for exploring and understanding the intricacy dynamics of the real-world phenomenon. Ultimately, advancing the both computational mathematics and our capacity to model the complex. So at this stage, we came up with this algorithm that was successfully applied to this type of problem. But we still know that there's more to do, especially when we have a complex problem, like some complex number problem, which we believe that this will be a starting point for this algorithm. And then we also even open the algorithm for collaborations so that we can come up with more robust algorithm that can handle both complex and not complex problem in complex problem in the applied and computational mathematics. We have the references, our references, we have a references 1 to 22, 21, and thanks for listening.
In the meantime, if anybody has any questions for any of the previous speakers, then now would be a good time.
I just have a general question, if I may.
Sure, yeah.
So in my research, I noticed that when you take something in Maple and paste into GeoGebra, it works perfectly. How is that possible? These are different platforms. Is it because GeoGebra was designed like this or Maple designed like this? How come that these two software are compatible with each other? And it is perfect compatible, like.
I don't know a definitive answer to that, but I have a theory. I must admit that I have not used GeoGebra much in the last 10 years, let's say. I know that copy and paste in Maple, it can work in several different modes, and one of them is using MathML. I would guess that maybe GeoGebra has the ability to, if you hit copy, to put the MathML version of the expression into the buffer, and that would be understood by Maple. But this is pure theory, not hindered by any practical experience.
Thank you.
Well, if anyone has final questions for the speakers.
And if not, then I will like to invite you all for the next program item, which will be the keynote by Dr. Laureano Gonzalez Vega, which will happen at 10:15 Eastern Standard Time.
Right, so about 20 minutes.
That's correct.
Okay, well, thanks everyone then for your for the speakers that presented and for the questions. And that will be the end of the algorithms and software stream. So yeah, thanks everyone for joining.